Welcome back to Structed. My name is Eric, and today we're here to talk about compact, non-compact, and slender steel sections. This is not a topic that generally gets a ton of emphasis during steel design courses, especially introductory ones, because so many of our standard hot rolled steel shapes do not need to worry about them. They're actually all compact. But as you get into plate girder design, or if you are reaching for some of the more legacy steel shapes or getting into forensic engineering type applications, you're going to start to need to actually know more about this. And especially if you branch out into things like light gauge steel or aluminum design, you start to have to worry about local buckling, which is what this slenderness classification is all about. But first, before we get too deep into that, I want to remind everybody that if you are studying up for the PE, SE, FE exams, or just looking for handy desk references, trying to learn new topics, our sponsor link down below in the video description will save you 15% off on a whole variety of things over at PPI2Pass, and it helps support this channel. So if you are thinking of any of those things, please head on over there. Here I've got drawn a heavy steel section and a much lighter one. This is actually not unreasonable proportions for some of our W shapes in our handy dandy steel manual. Your color may vary depending on which edition you're using, but the most current one is this lovely blue. So this is a heavy steel hot rolled shape. This is not something you'd find in there. You can see how slender this is, and the slenderness that we're talking about here, much like a tin can, as you step on it, can crush in and buckle locally. The walls can deform in and wiggle on you and crunch in long before you've actually exerted the 600 pounds or so it would take to actually yield that amount of steel or aluminum in a can. You crumple it under, I weigh less than 200 pounds and can't stand on a can anymore. And that's all due to buckling. Here, we're not talking about sidewalls of a can crunching in. We are instead talking about portions of the cross section deforming under loading in ways that we don't expect that can cause premature failure of our structure. So you've probably heard of lateral torsional buckling, where a whole beam kicks out to the side. We have paper, we can sketch that. In lateral torsional buckling, you're talking about having a beam shape, and I'm going to keep it simple here, but you've got a beam shape that I am doing a very poor job of drawing today. And we're supported on some form of a roller back here and a roller over here. And as we load up this beam with some form of transverse loading, if we're loading it in the stronger axis, this beam naturally wants to peel over, and kick out to the side. Just like if you take a ruler and you try to bend it in the strong axis, it's so stiff that it naturally kind of wants to kick to the side and give you problems. So it sort of kicks out and deforms laterally, and the torsional component is that for it to really align with the load, it wants to twist over and become more compliant in that way. It's kind of like a ball at the top of a hill. This energy state is very unstable. As you load it up, it wants to kick over. If we come back to our slender cross section here, a slender section, as I'm loading this beam, this is not even considering any local effects of putting your load out here on the wings of this or anything. This is far away from your load application point. You've got bending in this beam already, and you've got compression all across this flange. If we grab and look at our plane sections, remain plane, assumed strain distribution here, and stress distribution, this whole top part is in compression, and this whole bottom part is in tension. Under compression, this part is unstable. It kind of wants to wander on you. It could kick up, it could kick down. If we bend it the other way and put this in compression, you could get weird local sine waves and things. Just like a column or a beam that's being fully compressed, you've got a component here that is in compression and it wants to kick. If it is more slender, it has more ability to wander off. Here, this part kind of wants to kick, but it's got quite a stiff connection back to the overall body, so it's difficult for it to move out of the way. So this sort of thing here would be called flange local buckling. So I know I mentioned that we're not considering local effects. We're not considering local loading effects. So if I'm loading this right here and it's causing this flange to bend down, that's a different thing that needs to be looked at kind of as like a plate bending problem with either a cantilevered plate or a three-side supported plate, that sort of a thing. But we're also not talking about global buckling, which is when your whole beam section moves together in some sort of a kick out. Here we're talking about some local component of our cross section, be it the sidewall of a can or the little bit of this flange is wandering off. And this is important because if nothing else changes on this and this bends in, we lose stiffness. We've lost material being quite so far from the neutral axis. Flange local buckling can give you that premature failure from that. What can be even more devastating, though, is web local buckling. If the web kicks out to the side enough and becomes unstable, you can pancake the whole shape. And as we are all well aware by this point, a pancaked shape we've got a shape that initially looks something like this, where we've been good structural engineers. We put all of our heavy plate out here, and maybe this is, I don't know, half-inch steel. This is half-inch steel. But this metal isn't really doing that much. It's taking shear, and we don't have that much shear. We're in a bending controlled regime, a long span. We decided to make this, I don't know, 1/8 inch material. You can end up with a situation where you kind of squirt out and crush your web. And as it starts, it just continues and continues and continues because this becomes less and less stiff, less and less strong. Your material is no longer spread out, and you almost revert to nearly just a pair of plates sitting on top of each other if this goes too badly. And you could lose all shear flow through this and then really become just two plates at some small distance away from each other, and that's it. That is not nearly as strong as this. So if this happens, obviously, we would term it a failure. And it's going to be sudden and catastrophic. It's not going to be some nice, smooth bending over of your load displacement curve here. It's going to be more like up, 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 snap, with some critical buckling happening, going on, and just terminating you way short of where you expect. We want to avoid this. How do we avoid this? The steel construction manual that we talked about, this guy, for heavy steel shapes, uses classification of sections, and let's see if we can zoom this in. Doesn't look like this camera zooms. All right. Uses a classification of cross sections based on width to thickness ratio. So we end up with this lambda. Lambda equals T flange over B flange, or it might equal T web over H web. So these lambdas are taken either comparing that to that, or comparing your height to your thickness. And it's just looking at one part of this here. If you get into aluminum design, there's a whole multitude of different different considerations for flanges that are supported on one edge but free on the other, or flanges supported on one edge with a stiffener on the other edge, or flanges supported on both edges like in an HSS type shape or something like that. However, in this, all that we do is we compare these flexural member width to thickness ratios or slenderness ratios here to some limits that come from the specification back here in specification B4.1. Now these limits, you end up with a quite similar distribution here of a peak if you're compact shape, and this is, don't look at the close notes on this guy. These are all based on your unbraced length and your flexural torsion, lateral torsional buckling of a flexural member. But it is a similar shape, a similar regime for the compact, slender, and non-compact sections of our shape here, where instead of that, we end up with a few different lambda points here. We've got lambda, see here, lambda P, lambda R. And we've got an allowable strength up here. So you end up with a flat plateau and then a linear region and then a quickly declining higher order function portion here, depending on where your lambda is. So flipping back to B4.1, which I should have pre-bookmarked and did not, apologize. Specification. So we're in design requirements. We said B4.1, correct? I have this dog-eared in my edition and then went to a newer edition of the code. Of course, don't have everything bookmarked as well as I did in school. Here we go. With thickness ratios, compression elements subjected to axial compression. So this is not the one that we want. This is for local buckling of a compression member or a column. If we turn the page here, we have members subject to flexure. And hopefully we can get that to come into better focus. There we go. All right. So depending on your shape, we have with the thickness ratios that we're looking at in different locations, and we have these limiting these boundary cases between the types. So if we've got flanges of hot rolled I-shaped sections, channels, and T's, we're looking at these guys out here like we talked about, and we are comparing that with the thickness ratio to these different markers here. All right, so these are kind of the boundaries. So first thing that you want to do is find your slenderness ratio. Then you check between these boundaries, which are pretty constant. Most of your shapes are just going to be grade 50 steel these days, but it depends. Make sure that you are checking against that. So you come up with these boundaries, and then those will tell you on subsequent pages which equations to use. So you will check your limiting flange. Oftentimes you've got 4 flanges that are the same on an I-beam shape, but you might have a T or a C or whatever. And then you also have these different ratios and limits for your webs. The web checks are less likely to control, but they can. So then, of course, as these are flexural checks, we need to go back to chapter F for flexure. And there's a lovely summary table at the beginning of the chapter that you should definitely bookmark and become quite familiar with. This tells you what checks you need to look at. So you potentially have different slenderness for different shapes, and you have different limit states that can occur. So you've got lateral torsional buckling, and you've got flange local buckling for this shape if it's non-compact or slender in the flanges, and your web is compact. So your web is compact. That means that you are up on this plateau. So this is compact. This is non-compact. And this is slender. And those are all determined by what your slenderness ratio, B over T or H over T, is for that given check. So you check those based on your slenderness ratios that you have against those different dividers like we talked about, and this will tell you what your potential limit states are. So if you're a fully compact section here, your flanges are compact, your web is compact, your only limit states you need to check are yielding and lateral torsional buckling. That's it. If you have a non-compact or slender flange, you need to be checking for flange local buckling as well. If you have a compact, non-compact, slender, so any state for your flanges, and then your web is either compact or non-compact. You also need to be looking at some different limit states based on the potential for your web to buckle on you, and the list goes on. But these point us out to the various chapters here. And if we look at F3, doubly symmetric eye shape with compact webs and non-compact or slender flanges bent about their major axis, you've got compression, local buckling in your flange, and these are for your non-compact flanges or for your slender flanges. So again, you need to know which equation to reach for based on those slenderness ratios, and this little note right here tells you that all other ASTM W, S, and M shapes have compact flanges for Fy less than or equal to 50 KSI. So you've got this short list here that are subject to these provisions. Everything else is fine. That's what I'm talking about with having loads of shapes that this is not a concern for, but there are some legacy shapes that it is. Or if you're building up a section out of other shapes, also a possibility. Okay, so in summary, a shape is compact if all of the portions of the section are compact. If all the flanges, all the webs, any other features that could be slender are in fact compact, which is compactness at the this is the compact region, right? If all of the portions, every portion of this is compact, then this section is compact. However, if any component of the shape is non-compact or slender, then we name the whole shape based on the worst case. So depending on where you fall with your slenderness of all of your different components of your shape, you could have a shape that looks something like this. We've got thick, heavy webs sticking off. I don't know, maybe there's a thick, heavy one over here too. And then you've got this little slender piece sticking off. The whole shape becomes slender. And we call it slender so that we know that we need to go and use the appropriate equations from the steel manual, like we discussed. So again, the most odious part of this graph for any part of your cross section determines how the whole section is treated. So with that about wraps up what makes a shape in steel design compact, non-compact, or slender. Keep in mind this was all referring to flexural design. There are also local buckling concerns for compression design of a column, and we will hit on that in another video. If you want to catch that video or any others, please make sure you subscribe. If you enjoyed this, please like, leave comments below, questions, anything that you want to see covered. I would love to cover meaningful content for you guys. So And don't forget to check out our sponsor below. Thank you all for your time, and catch you on the next video.